Okay, so let's do a couple examples using the integral test. So the first infinite series we'll consider is the series from n equals 1 to infinity of 1 over n squared plus 1. Now, whenever we do a series convergence or divergence test, we always want to kind of go through the list of series tests that would be easier to use. So for example, the first test that we had was test for divergence. So let's just quickly go through that and see what it says. So if we do the test for divergence, we take the limit as n goes to infinity of our series function 1 over n squared plus 1, and that limit comes out to 0. Now, because this limit came out to 0, what this says is we get to do more work. And this was the reason why we started introducing more and more series tests. The second question we really ask ourselves is, well, is this series a geometric series? Because if it's geometric, we can easily figure out whether or not it's convergent. And for geometric series, remember, they have a very particular form of a series from 1 to infinity of ar to the n minus 1 power. And the way in which our series problem is written, there is no way in which we can write this 1 over n squared plus 1 term as just some number times another number to the n minus first power. So no, this series that we have is not looking geometric. So this is where we're going to jump into and do our integral test. And remember, to do the integral test, there's 3 things that we need to happen. As soon as we rewrite our continuous analog of our series function, which in this case will just be 1 over x squared plus 1, we need this function to satisfy 3 criteria. The first criteria is this function positive? And for x values within 1 to infinity, this function that we have is always going to be positive. As there's no sign changes, it never goes negative. This is always going to be a positive number. The second thing we have to decipher is whether or not it's continuous. And for us, again, in the same interval from x equals 1 to infinity, there is no x value that exists such that we'll get a divide by 0. So we get to say that f of x is continuous here as well. Now the third thing that we need to show is that this function is always decreasing. And remember, there's a couple different ways we can try to show a function's decreasing. We could do an algebraic route, or in this case, let's try to take the derivative to flex some of our Calc A muscles. So if we rewrite our function, f of x is equal to 1 over x squared plus 1, we could rewrite this doing the quantity x squared plus 1, all raised to the minus 1 power. And now if we take the derivative, we get a minus 1 coming down from the power. We have x squared plus 1 to the negative 2 power times the derivative of what's inside, which is 2x. So this whole product becomes minus 2x all over quantity x squared plus 1 to the 2. And for all x values, again, from 1 to infinity, this quantity is going to be less than 0. So it is indeed decreasing. So now that we have shown that our function satisfies these 3 criteria, we get to use the integral test. So remember, what the integral test was was we got to take the improper integral then from 1 to infinity of the continuous analog function to our series function itself, in this case 1 over x squared plus 1 dx. And if this improper integral converges, our series converges. If this improper integral diverges, then our series diverges as well. So in this case, we're just going to go ahead and take this improper integral. So the first thing we do is introduce a limit. Take a limit as c goes to infinity of the integral now from 1 to c of 1 over x squared plus 1. And now that we have introduced the limit, we can just go ahead and try to find that integrand's antiderivative, which in this case, hopefully you can recognize, this is just our friend, the arctangent. And I want to emphasize here, when doing this integral test, actually doing this step of finding the antiderivative, it may not be as trivial as it was here. You might have to do an integration by parts, a U substitution, a trig sub. But again, what I want to illustrate through this example is just our ability to use the integral test, show that the function passes the 3 criteria, perform the improper integral, and see what the improper integral does, because the series then will do the same thing. So in this case, let's plug in those integration bounds. So we still have the limit as c goes to infinity. Plugging in the bounds, we have this is the arctan of c minus the arctangent of the lower bound, which in this case is 1. And if you remember a lot of trig, the arctangent of 1 is pi over 4. And the limit as c goes to infinity of arctangent, this term actually comes out to pi over 2. So all in all, this entire integral then just becomes the difference between pi over 2 and pi over 4, which itself is equal to pi over 4. And since this number is finite, we get to say that this improper integral converges and through the integral test, we now get to say that our series also converges. So that's how to do the integral test. Again, whenever presented with a series and we're asking whether or not it converges or diverges, we ask ourselves, is there an easier test to do? In this case, we tried the test for divergence. And when we did the test for divergence, we showed we got a limit of 0, which said we got to do more work. We then asked, hey, is this a geometric series? Because if so, we could easily then figure out whether or not this series converges. Unfortunately, this series was not a geometric series. So then we went on and asked ourselves, well, what's the next test we can do? Well, that was the integral test. And the benefit for the integral test is we can apply it to a lot more series due to lower restrictions on what the series has to be. In other words, it doesn't have to fit this very particular form for a geometric series. Before we go on to the next example, I just want to briefly remind us what the plot of the arctangent function looks like. So if we're trying to plot the arctangent of x, what this function looks like is that as we approach from 0 to infinity, it increases, but then it asymptotically tapers off. And it does a similar thing going from 0 to negative infinity. It goes from 0, and then asymptotically tapers off. And where it happens to taper off are at the values of pi over 2 and negative pi over 2. So that's just what arctangent looks like. Okay, let's move on to another example using the integral test. For this example, consider the following series. The infinite series from n equals 1 to infinity of 3 over 2n minus 1. And again, we go through our grab bag of series convergence and divergence tests. So the first test we do, test for divergence. Can we just do a limit and see if this series is divergent from the get-go? So we take the limit as n goes to infinity of 3 over 2n minus 1. And lo and behold, that denominator is getting very, very large, while that numerator is just a finite number. So the denominator wins, and this whole thing is going towards 0. And again, because this is 0, we get to do more work. The series passes the test for divergence, but again, we have to do more work to actually figure out whether or not it converges or whether or not it diverges. And we just, of course, ask ourselves very quickly, hey, is this a geometric series? If so, we could ascertain whether or not this is convergent or divergent. But remember, a geometric series has the very restricted form of some number that we called a times another number raised to the n minus first power. And in this case, our series, it's not a geometric series. So we get to move on, and at this point, the only other option we have is integral test. And the first thing we do for integral test is think about what the continuous version of our series function would look like. In other words, basically just swap out all of the n's for x's, which we're swapping a discrete variable n for a continuous variable x. And we need this function f of x to satisfy 3 criteria. The first criteria, hey, is this function f of x positive? And in this case, for all x values greater than 1, going off to infinity, this function f of x is positive. And again, the reason why we care about x being greater than 1 is because our series is starting at n equals 1 and then going all the way to infinity. If our series were to start at, say, n equals 17, then we'd care about this being positive for x values greater than 17. We also need this function to be continuous. And for us, what this really asks is, hey, are there any points in which we get a divide by 0? And in this particular problem, where we get a divide by 0, actually happens at x equals 1/2. So for continuity here, we're really asking ourselves, when does this function, or the denominator of this function, equal 0? And here, it's when x equals 1/2, which is not in our interval. So this function is continuous like it is positive. And finally, the third thing we need to show is that this function f of x is decreasing. And to do this, we're just going to take a derivative of this function and ask, hey, is this derivative always negative for x values greater than 1? So f of x we can rewrite as 3 times 2x minus 1, all raised to the minus first power. So let's take the derivative. F prime of x equals 3 times negative 1 times a 2x minus 1 to the minus 2 through power rule. And then through chain rule, we get this factor of 2 coming from the derivative of the inside. So, in other words, the derivative of our function f of x is equal to minus 6 all over the quantity 2x minus 1 squared. And for all x values greater than 1, this indeed is less than 0. So our function is also decreasing. So now that we've shown that our function satisfies these 3 criteria, we can go ahead and actually implement the rest of the integral test, which is performing that improper integral. So let's do that now. So we go ahead and perform the improper integral from 1 to infinity of our function, which in this case is 3 all over 2x minus 1. Oops. Let's clean that up a bit. Not any better. And the first thing we do for improper integrals is introduce a limit. So we'll take the limit as c goes to infinity of the integral now between 1 and c of 3 over 2x minus 1. And now that we've introduced this limit, we can go ahead and compute the antiderivative. Before we do that, I just want to give us the vision of what we're trying to do. Remember, for the integral test, when we get to the point of the improper integral, if this improper integral converges, we get to say that our series also converges. Similarly, if the improper integral diverges, we get to say that our series also diverges. So let's go ahead and do this antiderivative. Looking at this, we can do a nice u sub and let u equal 2x minus 1. The derivative is equal to 2 dx. And then we can substitute this into the integral. Our bounds are still going to be with respect to c instead of u. But if we substitute this into the integral, we now have this as the integral of 3 all over u times du over 2. And this is an integral that we can just go ahead and anti-differentiate. So this is the limit is still going to remain. We have the limit as c goes to infinity. But the antiderivative that we'll get is this factor of 3 halves out in front times the ln of u. And again, we evaluate that at x equals 1 and x equals c. But remember, our bounds of the integral are with respect to x, so we have to go ahead and resubstitute in for u to get in terms of x. So just resubstituting in what u was equal to 2x minus 1. And now we're at the point where we can just go ahead and put in the integration bounds, 1 and c. So let's go ahead and do that. So we have the limit as c goes to infinity of 3 halves times the ln of 2 times c minus 1 minus 3 halves times the ln of 2 times 1 minus 1. So let's just do a little bit of arithmetic. So we have, this is still the limit as c goes to infinity of 3 halves of ln of 2c minus 1 minus 3 halves times the ln of 1. So we're at the stage now of where we get to just compute the limit and basically see whatever we have left over. And notice this term on the right, this has no c's in it, so it's not affected by the limit at all. In fact, if you remember, the ln of 1 is actually just equal to 0, so there's no contribution from any constant term without a c. But this limit, as c goes to infinity, the ln of 2c minus 1, that's also going to go to infinity. So this limit is actually equal to infinity. And now, because we've just showed that the improper integral diverges, we can automatically also say that our series also diverges. And that's how we can do the integral test. And also, before we move on, just in case you want to remember what the ln of x looks like, if we make a plot of the ln of x versus x, well, we just know at when x is equal to 1, ln of x is equal to 0. But as x grows beyond 1, the ln of x is also going to grow towards infinity, just very slowly. But as x goes from 1 towards 0, this is also going to negative infinity between 1 and 0.